Okay. All right, hello everyone. Let's get started. Someone just said I use this joke all the time, but it usually works. So let's see how it works today. I'm vertically challenged. I don't scale up or out as good as Couchbase, so I'll try to be here on the side so you can see me as well as the slides in the back. Looks like it kind of worked. So a little bit about me, Dipti Borkar. I've been with Couchbase many years. I used to manage the product management side, and I now run the solutions engineering team in the sales organization. And so today's agenda, I wanted to talk about where Couchbase fits in, some of the key concepts, how do the operations work on a single node and a cluster-wide basis, as well as, if time permits, a look at the live cluster. Looks like we're running a little bit late today, so we'll see how that goes. And I think for some of you, today might be the first time you are getting introduced to Couchbase or going a little bit deeper into Couchbase. So hopefully at the end of the session, you'll walk away with where it's a good fit, how it works at a high level, and then what are some of the details of the insights, right? How do they work? And then what are the key characteristics? What are the features? And a little bit about 4.0, particularly Nickel. So in the grand scheme of big data is an overloaded term. It means many things. But there's two key categories or two key areas of big data. One is the analytics side, and that gets a lot of attention with Hadoop, the Hadoop ecosystem around it. But there's also the operational side of big data, which is where NoSQL fits in, and which is where Couchbase fits in. This is where you have, you need to build applications for mobile, for web, for IoT, and that's where Couchbase is the backend for those type of applications that need performance, that need scalability, as well as high availability. And Couchbase has those characteristics, and so those are some of the key characteristics of Couchbase. We do really well at scale with performance. Performance is both low latencies as well as high throughput, so it's that combination. We are very, very easy to scale out. As you'll see in many of the demos today, you can click a button and you add a node or you remove a node, you click another button, you rebalance the cluster. And it's very, very easy to manage from an administrator's perspective. So even though it might be a new technology for many of you, having a system that's just easy to manage makes it that much easier to adopt and use as well. High availability is obviously very important for mission-critical applications. A lot of you come from the enterprise world where you are building things that run, and there's money that is made from those kind of systems. And you need it up and running 24/7, which means HA within the cluster, DR across data centers, across clusters, maybe rack awareness, zone awareness, and all of those capabilities are a part of Couchbase, and I'll touch on a few of those today. And finally, the fourth key characteristic is a flexible data model, which basically means we use JSON natively. So we natively store JSON, and not rows and columns and not tables. And this gives you the flexibility of representing fairly complex objects in the real world because of the flexibility of JSON. It could be a hotel, which includes the hotel name, description. Some hotels might have some amenities, others don't. And so the object of the hotel needs a flexible schema that can work with it and grow with it as needed. And that's where JSON comes in. So it's a flexible data model which allows you to move fast along with the functional changes in the application, make changes to the data as you go. So you don't need complex alter table statements that need downtime associated with relational databases. And so you can add attributes on the fly to your JSON data and keep going. And so the document model in general is one we've seen to be the most flexible and the broadest of all to support a wide range of applications. Now, in terms of the use cases that Couchbase supports, there's many use cases, but these are the 10 that I'd like to highlight. We're great at profile management, personalization, These are where you need fast access to the information. Performance is really important. You also need flexibility of JSON that I just talked about. There's also the real-time big data side, and there's a lot of sessions today where customers will talk to you about how they use Couchbase along with Hadoop. So while Hadoop is being used on the big data side a lot, there is also a real-time aspect of big data, which is the speed layer that a lot of people are talking about. And Couchbase is a great fit for the speed layer. This includes ingestion of fast coming in information, whether it's sensor data or device data, or it could be doing some lightweight real-time analytics on this information that is newer, the latest information that's coming in, so that you can have some insights on the most recent one. And then you can do the heavyweight batch loading or batch analysis on the Hadoop side of the cluster. So the real-time big data use cases are also becoming very popular for Couchbase. But let's jump into some of the key concepts, right? So at a core, Couchbase can be used in many different flavors. These are just two of them, but you can use us as a cache, you can use us as a key value store or a document store. But in theory, the point is that you have a key or a unique identifier that identifies a value, and that value could either be a blob, like you have in a relational database, or it could be JSON. So on the left, you see that it's just a blob, right? There's some bits in there that the database doesn't understand. But on the right-hand side, you have JSON, which is actually a nicely formed document with attributes in there. And then you can do more with it, like create views on top of it, like use Nickel on top of it. And so there's many things that you can obviously do using JSON. So you can use it in both these forms, yes. It doesn't matter. A single bucket, and I'll talk about that in just a minute. A bucket in Couchbase is equivalent to a database. It's the equivalent of storing many, many tables into one database, right? And so you might have one object that's a blob. You might have another object that's a JSON document, all mixed up in the same document. So that the flexibility is not only using JSON, but the flexibility is also storing different types of objects in a single bucket. And I'll try to repeat the question since you may not hear it at the back. The question was, can I have both these types together, or do I need separation to use it as a key value store or a document store? And it doesn't really matter. Your access as an application developer is using a key, and the value can either be a blob or a JSON document. So when you look at the key aspects of data, you have the document ID or a key that I just talked about. It's similar to the primary key in a relational database, right, in some ways. And then we partition data using this ID, this document ID or this key, and it can be, and key value lookups are very fast because we have a memory-first architecture. A lot of the data resides in memory, and so when you look up a key, you have immediate access to that hash table where it resides in memory, and you get back the value. And so we're talking a couple of milliseconds of response time given the way the architecture is set up. And we'll look at the architecture in just a little bit. And then you have the value that I talked about. We also have, and you can store things like serialized objects, serialized Java objects. Some customers store compressed XML. Some customers store encrypted values. Whatever it is that you want to store for fast access, you can store that as a blob. There's a bunch of metadata that we generate ourselves that is used in many different ways. CAS is the check and swap value, which is used for optimistic locking, if you want to have optimistic locking in your application. And then your TTL is a time to live. So if you want a document to expire after an hour, you can use this so that you can set it up on a per document basis. So it's very fine granularity. So over time, you can have data expiring very, very seamlessly, and you can manage that efficiently. So I talked a little bit about benefits of JSON. So let's get into the concepts. So you're at the client or a user application layer, you are using documents, right? And these documents live on data buckets, as I mentioned. The data buckets then live on physical servers, the server nodes, and the servers together form a Couchbase cluster, right? So that's the simple hierarchy of the data. Now, the cluster, the way we partition data is based on hash partitioning. And so we take that ID or the document ID, the key that comes in, and hash it and see which partition it lives on. But from an application developer's perspective, you're just dealing with objects or you're just dealing with JSON, right? So when you add data into the system, you will just store it as JSON, and then you get it back as JSON. You don't really see where that data lives. Is it a 10-node cluster at the back? Is it a 100-node cluster at the back? All of that is completely transparent to you because the client SDK takes care of all those details, right? So in terms of range of technical use cases, as I mentioned earlier, we have high availability, key value stores, and so on, as well as an embedded database on the device that I won't talk about here, but there are mobile sessions that go into more details about that. And then we have a sync gateway that sits between the embedded database on your device and Couchbase server in the cloud to sync data back and forth. And it's extremely seamless. It's very easy to build mobile applications with this. So now let's look at the various operations. Let's look at a single node operation and then look at it across the cluster. Every node in Couchbase is identical. So you don't have a config S or a master or a slave or an administrator or an arbiter node. All nodes look the same, and they look like this, right? So you have the data manager, which obviously manages the data portion. It includes data access, query access, indexing, and then you have the cluster manager, which takes care of all the cluster-wide activities. So the cluster manager is responsible for rebalancing, replication of data, and various other cluster operations. So now let's take a look at what actually happens when you read and write from the system. So when a document comes in, the first thing that happens is it gets stored into the managed cache, right? The managed cache then, from there, it gets pushed into the replication queue, as well as what we call the disk write queues, to get persisted down to disk. Because of this asynchronous nature, when you write the document, you have immediate access to it because it's already in memory, and we don't wait for it to persist to disk. So when you have data that's all in memory as you're writing to it, the speed of reads can be extremely fast. Now go ahead. Sure. So let's talk about that here. So obviously, the question is, well, some data I could do this for and have it asynchronously persisted to disk, but some data is very important, right? If I have PII information that's really important, I want to make sure it's written somewhere, or it at least has another copy of it somewhere else. So you have the option of saying what you want to do with it. Do you want it to persist to disk and wait until that point? Do you want it to be replicated to another node in the cluster? Or maybe you want it to be replicated to 2 other nodes in the cluster. And so you have the option of telling the system what you want to do with it. Okay? So read operations are simple. You read from if it's in memory, you just read it back out of memory. And if it does happen to be on disk, and we've had a cache ejection, which means that there's a lot more data that can fit in memory, obviously we have to take off some of the older data from memory, but it still resides on disk, right? So in this case, we eject data using a multi-bit, not recently used algorithm that actually keeps track of how hot that data is, how warm that data is, how cold that data is, and then we do cache ejections based on that algorithm. And in case of a cache miss, if the data is not in memory, it gets pulled back up and gets sent back to the application. So now let's look at the more fun part, which is the cluster-wide operations. So single node, it's really easy to read and write. When you are reading data and writing data, you use the APIs. And whether you're writing to a single node or 100 nodes, it really looks the same. There's no change in the code from the application perspective that needs to change. So let's talk about sharding. There's 2 ways of sharding typically. You can do range partitioning, where you have, let's say you have 5 nodes and you have A to E on one node, and the keys starting with F to K on another, and so on. And that leads to creating hotspots, because you might have Apple, which is incredibly popular, and you keep hitting the first server. But what you want is a more uniformly distributed workload, and that's why we use hash partitioning. So we partition our data into 1024 virtual buckets. So a single data bucket is partitioned into 1024, and each of these live on some physical server. The map between the logical partitions, or the V buckets, and the physical server that it actually lives on is called the cluster map. This cluster map is really kind of the secret sauce of the system, which tells every component of the system where data lives. And we look at an example in just a minute. So when you have the application saying, hey, can you get me access to this specific key, the client SDK takes a look at the key, it does a hash of that key, and then it looks up the cluster map and sees which server it lives on. In this case, if it lives on server 1, it's going to go and hit server 1 and get that request back. If it lives on server 3, it's going to go directly to server 3 and get that request back. So there is no indirection, and it's extremely efficient in the way it's managing and accessing data. But more interestingly, if you add more nodes to the server, and you have 5 nodes instead of 3, then the cluster map is automatically updated in a couple of different ways. And you have this, that's a part of the client SDK, which will now know that this data that you are looking for lives on a new node, which is server 5, and will go and directly access data from server 5. So it's seamless from an application perspective, and this cluster map is really the secret sauce in the way how the system knows where the data lives, which node it lives on, and this cluster map is used not just for reading and writing data, but it's also used for other features like replication, cross-data center replication, and so on. So in Couchbase, we allow you, even though all nodes are equal, you obviously have replicas. So you need high availability, and you have the option of creating replicas. In this case, you have one replica. So let's say you have a replica of data that lives on another server. You can have up to 3 replicas. So you have four copies of data that are available to you. In case a node goes down, you have another copy available. So you have high availability with our intra-cluster replication technology. Now, when you are adding nodes to the server, this operation is an online operation. So the rebalance operation, where we can add multiple nodes to the server at a time and grow the cluster, is all online while your application is running. So there's absolutely no downtime. So let's add 2 more servers to this cluster. Again, you have your active and replica data. And when you hit the rebalance operation, that's when the data starts moving around. This is done in increments in the basis of the V buckets that we have, the virtual buckets. And so it's an incremental operation. If it fails, if it stops in the middle, you don't have to start from the very beginning. Your new servers are already managing some parts of data, and then you continue from the point of view where you left off and keep going. So it's a it's a throttled operation to some extent, so there's less impact on your front-end application. But it's also all online, and it's incremental, so that in case of failures, you can continue from where you left off. Now, when the topology changes, the cluster map gets updated as well. This includes in the client SDKs. And then the client knows which server to actually go and access that data from. So that's how a cluster works. That's how cluster topologies change, and how the clients know where the data lives and how to access it. So now let's take a look at managing failures. So in case of failures, usually things are going great. All is well. The app is going steady, and then the disk fails, right? Or the OS has a crash, or bug in Couchbase. Never happens, but sometimes it's code. There's a Couchbase down situation. But in any case, in case of that, you don't have to worry because you have a replica. Or you could have multiple replicas available. And you can fail over that node that went down. You can either do it manually, because you might have more insight into monitoring the system, or you can do it automatically and have Couchbase determine that the node is down. in that case, the nodes, the partitions that I was talking about get promoted to active, and you're back up. So you have full data availability, even though you have a node down. Now, in this situation, you still have some data without a copy of your replica now, right? Because you have a node down. And that's where you rebalance the cluster. When you rebalance the clusters, the replicas get recreated. The data also gets uniformly distributed across the cluster. So you have a couple of options. You can remove this server from the cluster and move to a 4-node cluster temporarily until you can add more hardware, right? Or you remove this node, you add 2 more nodes because it turns out you really need more capacity, and do it all together, hit rebalance, and you're back to having replicas for all your data, and you're back to having more capacity. So the good part about Couchbase is you have the flexibility to add different types of nodes, 1 node, remove 2 nodes, or even add and remove the same number of nodes so that you have a very efficient swap across those and have a mirrored rebalance that takes place. Yes.
The replica is always on a different server.
Yes.
From its origin. And 2,
Just a moment. There's a question here.
And 2, if you've got like a flip-flop situation, can you delay the rebalance because you might bring that server back up?
Yes. Sure. So the question is the replica always on a separate server for a separate physical server? It depends on your situation. If you have a 2-node cluster, right, and 1 node goes down, you don't have a copy of your data, you have only 1 copy. But if you have a 4-node cluster, yes, your 1 copy of data is guaranteed to be on a separate physical server. In addition to that, we have a feature called rack zone awareness. And so if you actually know where your physical servers live, you can create logical groups associated with these nodes and say that I have 2 racks, even if you don't, right, and I have 2 physical servers, and have the replicas created on the other side. So even if one entire rack goes down, and you have only one replica, you have full availability of data because whether it's 6 nodes go down or 12 nodes go down, you have all the replicas on a different physical box. And then the second question was,
can you
delay rebalance. So when a failure happens and a node goes down, you obviously want your data availability. That is the primary requirement. That happens automatically, so you don't have to deal with it. The rebalance operation, on the other hand, is not automatic. And there's obviously a reason for it, because there's movement of data. You want to do it at a period of time where it's not peak. You want to do it 2 a.m., at some point at night. And so, yes, the rebalance operation is not automatic. After a failover, we give you the choice of figuring out how to do that. So now let's take a look at cross-data center replication. This is one of the highlights of Couchbase. It's really incredibly easy to take data from one entire cluster and send it over to another data center, right? The data center could be in the same city. We have a customer who has 2 clusters in 2 different data centers in San Jose, right? Just right next to each other because they just need the extra capacity. Or you can have data centers located across the world. So you might have a data center in Phoenix, and then you have another one in Ireland, and another one in Singapore, and you have XDCR across them. So XDCR is something that not only gives you data locality, which is take your data to where your users are actually located, but it also gives you disaster recovery. So in case of failures, your data center goes down, you have the complete data set available in another data center. Now, XDCR is a memory-to-memory operation. So as we saw earlier, when a write comes in, right, we wrote it to memory, it asynchronously got persisted to disk, but we don't wait to ship it off to the other cluster until it's written to disk. As soon as it hits memory, we ship that information off to the other data center. In fact, we send that mutation to every other component in the system. We send it over to our view engine. We send it to the nickel engine, the index engine, the global secondary indexes. We send it over to XDCR. And so all these operations are basically memory to memory. The stream is coming in memory, and they get notified in memory. And so there's no delay from a persistence perspective. It's completely, in some sets, independent of disk speeds. from a CAP theorem perspective, that's not the CAP that I'm talking about. CAP is consistency, availability, and partition tolerance, and I think many of you here will be familiar with that. From a physics perspective, you can only get 2 of those 3, right? So you can either have a CP system or you can have an AP system. It's very difficult. It's impossible to essentially have all 3. Within a Couchbase cluster, Couchbase is a CP system. It is strongly consistent within the cluster. So when you write data, you only write to one location, which means that when you read data, you're not getting older copies, you're getting the most recent copy. In this, it's different from the way some other systems like Cassandra or React work, which are eventually consistent. So we are strongly consistent within a cluster. However, to have strong consistency across clusters and maybe across the WAN is not the best thing to do, because that means synchronous replication, and you're waiting for an operation to be sent over the WAN. And so when we have XDCR and we have 2 clusters or 3 clusters or 4 clusters, we become an AP system. We have availability across the clusters and partition tolerance. And so a CP system gets transformed into an AP system with XDCR. So depending on your requirements, you can have a very strong consistency app built in a single data center. And then you have XDCR available to you for data locality as well as for disaster recovery. And that becomes an eventually consistent scenario where the data comes into one cluster, it gets sent to the other cluster, and there is obviously a delay given that it's going over a WAN. Right? Now, XDCR is very flexible. So you can have unidirectional XDCR, most basic, A to B, right? You can have bidirectional replication, A to B, and then B to A, right? Both have both sets of data. Different use cases. If you want a hot standby, all you need is unidirectional replication. If you want an active setup, then XDCR bidirectional, so you can write to both locations, and that data is getting sent both ways as well. Or you can have complex topologies like the one shown here, where you have propagation down to maybe regional or local data centers. Or maybe you have aggregation, where if you have factories in Asia and you're collecting information from there back to your headquarters in the valley, then you can have information collected from various data centers remotely into one big data center. Question?
Is your replication statement-based, or is it at a block level?
Good question. So the question is replication statement-based or a block level or something else? So typically with a relational database, it's log-based, right? So you replay your logs for replication. We don't do that because logs inherently slow the system down. Replication is based on a permutation basis. So as mutations come in, they get streamed over to the other side, and it's all happening in parallel. So every node is talking with every other node on the other side of the cluster. And it's not just one stream, it's 16 streams by default, and you can grow that up or shrink that down based on the capacity on the other side. So you can have very high write workloads that are pushing in data, shoving in data into a 10-node or a 5-node Couchbase cluster, and that is seamlessly being shipped over to the other cluster because it's highly, highly parallelized. Okay? So it's you can think of it as mutation-based. It's a live stream. It's the same stream that we use to communicate across with other components. Yeah, so it's the DCP protocol, so it's the database change protocol, which is basically streaming information into XDCR. Now, this, in terms of, so it's highly, you can scale out horizontally. So you add, if you want to increase XDCR throughput, you add more nodes and you can just scale out, or you can increase the number of streams if you have higher CPU boxes, right? So you can scale up or out for XDCR. So let's actually take a look at how it works. So when a document comes in to the managed cache, as we saw earlier, it gets pushed into the intra-replication queue. So this is just from one node in a cluster to another node in the cluster. It also gets pushed into the disk write queue, but now we're also shipping it over for XDCR to perhaps another data center, another country, somewhere else. And so all of this happens in memory without paying the price of persisting to disk, and it's all asynchronous. Now let's take a quick look at indexing and querying. So we have two kinds of indexes with Couchbase Server 4.0. In the current version, 3.0, we have in materialized views, which are incremental map-reduced based indexes. You can think of it as similar to a materialized view in a relational database, right? So you basically create a view on a subset of data, and then you query it. So it's pre-computed, even aggregations are pre-computed, and it's really powerful for lightweight real-time analytics. And these indexes are kept local to the data. So they're local indexes. They live on the same node where the data lives. So this is how it works. So when a document comes in, it gets shipped over, as we saw, to the other queues, but now also hits the view engine that we talked about. And then that goes down to disk, and the view actually gets created on disk. So your index is persisted on disk, and you can have operating system cache that takes care of getting that information back in memory for a query that comes in. So now when you look at it across the cluster, you have 3 nodes in the server. You have your active and replica data, but now you also have the local index. So you have the active index, and you can also have the option of a replica index. And then when you query the system, you can query any node in the cluster. Right? All nodes are equal. You can talk to any node. That, in this case, server 2 becomes the coordinator for this query. It says, OK, I'll be the coordinator for this query. I'll go and look up what data is needed, filter that data, get it back, and then send it to the client. So it sends out a request to the other nodes, goes to the index trees, the B trees, gets back that information, and sends it back to the client. Right? So that's the way indexes with views work in 3.0. Let's talk about some of the other indexes, and then let's take a look at how nickel and the nickel indexes work, the secondary indexes work along with it. So we do have connectors to full text search. So along with your data access, your standard structured queries, you might need some access to text search, full text search, reverse index, right? So Elasticsearch, Solr, they're both, we support connectors to both. And essentially, it's using the XDCR stream to send it to another cluster, so an Elasticsearch cluster or a LucidWorks Solr cluster.
So your full text search is not within Couchbase?
Yes. So the question is full text search is not a part of the Couchbase cluster. At the moment, yes. So we have, these systems are really good at what they do. They do full text search well. And so we ship the mutations over to these systems to give you a full range of capabilities. But there is a session at Connect, which is about full text search, and through our labs, our Couchbase labs. And so that's something that we'll have over time. So that's the Elasticsearch connector. The Solr connector is similar as well. And that takes us to 4.0. So as many of you heard today at the keynote with Ravi, let me just stop and ask a question at the back. Yeah. Yes. Good question. So the question is, if you have XDCR, if you're using an Elasticsearch connector to ship it to the Elasticsearch or Solr boxes, is there a way to keep that consistent in some sense? So the way these connectors are built is we basically try to mimic a Couchbase cluster on the other side. So while it's actually Elasticsearch, the connector thinks it's actually Couchbase. And so it's sending over data to Elasticsearch, thinking that it's a Couchbase cluster. And it's a one-way replication, right? So typically, Couchbase sits on the front. It's very good at ingesting high speeds of data, reads and writes as well. Elasticsearch might be good at the full text search type of relevance-based queries, right? There is a mapping across the two that you create when you configure it. And so you configure it to a specific index on Elasticsearch that it gets replicated to. Now, given that XDCR is incremental, like are many other components of the system, if it goes down, it doesn't have to start over again from the very beginning, because we maintain checkpoints in terms of where it left off. And so it will just check metadata on the other side and what it had, and then it will just do the delta to send over to the other side. Okay? So why SQL for NoSQL, right? It's a question that we get very often these days, and one that is not necessarily that easy for the relational folks, right? With the relational mindset to really understand. But when you look at NoSQL, what NoSQL essentially is a flexible database that's scalable, that's performant, but it does need a way to query information. The best way to query information is using some sort of a structured language where you don't need to know what that data looks like, right? But you have the flexibility of telling it, give me this, and it gets you back that data. And so we've adopted SQL because it's every tool understands SQL, millions of people understand SQL. There's a huge ecosystem around it, but adapted that to JSON. So we've extended SQL to add specific characteristics, to use the hierarchical structure of JSON, to nest and unnest, to find data and attributes that are nested deep within that JSON, and give that flexibility to users. So when you look at a SQL statement, when you look at a nickel statement, you might even think it's a SQL statement because it looks and feels the same. But when you look at some of the extensions, that's when you get the real power along with JSON and SQL together. Yes. With the relational databases, the way I look at it, I come from the relational database. I wrote code for DB2 in the index kernel for LUW. And these databases started off with the query. They added replication, and they added scalability afterwards. We focused on scalability and performance at distributed data, and now we're adding the queryability now that we have the foundations right, is one way of looking at it. But here's just a quick slide to kind of show the difference. It obviously gives you a lot more flexibility with JSON, with your schema in the way you can represent objects. And as I was saying, here's the details of what we include: select from where, group by, order by, all the basic things that you would expect. We support joins, as you saw this morning, subqueries, nest, unnest. We even have a prepared statement that you could use in your application. Aggregations, all the basic aggregations, union, intersect, except. So that's kind of a full range of the select statements, the clauses that we support. Good question. So we have UDFs in the plan. UDFs is kind of the start to stored procedures and so on. But stored procedures is one where it starts becoming a little bit of a program. It's more programming than just a query language. Next question is, can you support PL SQL? And we really don't want to go there at this point. What we do want to do is expose this to everyone, see what people get with it, the kind of applications that people are building. There are some fundamental business requirements like triggers, right? Like different types of things which are not specific to a relational data model, which can be applied to any system. And those are the kind of things that we will have. The things which are basic business requirements that you need from an application perspective, those are really features of Nickel that we will try to plan ahead in the future. Okay? Now, in terms of the architecture, given our multi-dimensional scaling, you can have a single cluster of Couchbase, each node running a data service, a query service, and an index service. Or you can have a cluster where you have some nodes running the data service, some nodes running the query service, and some nodes running the index service, so that you can scale your hardware based on your workloads. Key value access and key value data access doesn't require a whole bunch of CPU, right? It needs memory, and it needs pretty decent disk if you have a high write workload. So you could have spinning disk, or you have SSDs on the back. But your index workload, on the other hand, is extremely I/O sensitive and needs a lot of resources. Your query workload needs a lot of CPU. And so you can have hardware based on those profiles to have these services running on the appropriate hardware. In terms of indexing, you can create different types of indexes. So you can use the create index statement. You can either create a view, or you can create a global secondary index, which is new in 4.0. And then this can be a pretty complex index as well. So you can have a JavaScript function that represents a view, or you can have an expression in your global secondary index to represent which attribute you want to index out of that JSON. And we obviously have the explain as well, so that when you run the query, you can see what the plan looks like. So it's a pretty simple optimizer at this point. I mean, the relational world took 30 years to get to an extremely advanced optimizer. But you have hints available if you want to use specific index so that it's most efficient. And we do have DML as well, so update, delete, insert, etc. This is experimental in 4.0, but it's something that we will productize as GA in the future. And with that, thank you very much. Let's take some questions now. Thanks, everyone. Sorry, say that again? Yeah, so the question is, how are requests distributed to the server nodes? When you have, when a request comes in, it takes a look at which vBucket or partition it lives on, and it goes to that node, the client SDK. The client SDK has the logic that takes care of the hash partitioning. No, the client SDK lives with your application, so it's like a driver. It's equivalent to a JDBC driver, right? So it's your Java client, your .NET client, your Node client, whatever client you're using, that has the logic to tell you where that data lives. And essentially, since we use a hash distribution, the workload is distributed across the cluster, uniformly distributed across. Maybe we can talk offline if you have a specific use case. Can't hear you too well. All right, any other questions? Time for lunch? All right, thanks, everyone. Say that again? Yes, yes. Absolutely.
I manage the data platform.
Very nice to meet you.
You probably know Santosh.
Yes, I've met